In this presentation, I will showcase some of the work conducted as part of an EPSRC Prosperity Partnership on smart pulses for subsurface engineering, in which we aim to develop best practices for efficient reservoir stimulation whilst minimizing the risk of induced seismicity. Here, we performed a series of uniaxial compression and Brazilian tensile strength measurements at a range of deformation rates in order to understand the impact of strain rate on material strength, system permeability, and geophysical signals associated with deformation via acoustic emission monitoring. Using a dense, low permeability, medium fine-grained granite, we performed compressive and tensile strength measurements at 4 strain rates, or diametric equivalent strain rates in the case of Brazil disc tests, from the standard rate of 10 to the minus 5 up to 10 to the minus 2. Sample failure was achieved in anything from over 1,000 seconds to under 1 second at the fastest rate. We found a significant rate strengthening effect whereby compressive and tensile strength both increased by approximately 35% across the 4 orders of magnitude of strain rate tested. We found that the static Young's modulus remained relatively constant across this range of deformation rates. However, the variability of Young's modulus from sample to sample was reduced at faster rates, owing to the reduced time for equilibration of the system to impose stresses. Acoustic emission monitoring showed different progression of fracture initiation, propagation, and coalescence in compression and tension, and also differed as a function of deformation rate. Slower tests were characterized by more frequent, smaller amplitude events, which increased in number and amplitude towards failure, whereas faster tests were characterized by fewer, larger events. This served to substantially reduce B-value from that measured at the slowest rate in both compression and tension. Increasing deformation rate resulted in increasingly localized rupture of the samples, which corresponded to the pattern of released acoustic emissions. The presence of a fracture, especially in initially dense materials, can increase permeability by many orders of magnitude. More complex fractures or fracture networks are more likely to prop open and maintain permeability, whereas planar fractures may close efficiently. This suggests that fracture networks in both natural and engineered environments, generated more gradually, may offer greater permeability enhancement and greater longevity of fracture conductivity, with the added bonus that lower magnitude stress drops and lower peak amplitudes of seismicity may also dominate during their creation.